my pleasure to welcome Gusz Eiben today as a guest speaker in our weekend seminar. He's a professor of computer science, I think, at the Free University of Amsterdam in Holland. And even though he's originally trained as a mathematician, like many of us, he decided that there's interesting things to be learned in biology and engineering. Sam, could you mute your mic, please? Is that not Sam?
Yes, sir. Yeah, that's Sam.
Sam, can you mute the mic there, or can you guys mute your mics, please?
And
yeah, it was unmuted for a moment, sorry.
Thank you.
So he has been passionate about using evolution as a tool to understand and, in fact, one day create intelligence, just as we did here in our course. And he has taken a tack that actually has much more hardware in it than we usually have. And he's going to talk about embodied evolutionary computing.
Thank you very much. It's really a great pleasure to be here. Thank you for inviting me and giving me this exciting 2 days. As a very slight correction, I'm indeed a professor in Amsterdam at the EU University, but since July or August, I'm also visiting professor at the University of York at the electrical engineering department, where they also want to have embodied intelligence, and they call me for the intelligence part somehow. I also checked it a minute ago that the address, that if you type me in Google, you can really find me on the first page. So when I did this for the first time, I thought it was relevant to just say Google Eiben, and I thought I have to put up my email address. But it was in Germany. And I said, just Google Eiben, and I will be the first hit. And the next day I was lecturing again for the same audience, and the student said, sir, I checked it, you are number 25. Who are the first 24? As it happens, Eibenbahn in Germany is a certain tree, so the first 24 were about gardening. I checked it a minute ago. Here is my competitor Kevin Eiben, who is a football player or something. I've never heard of, but still I'm on the first page. You can find all my data by it. So I will tell you a bit about embodied evolution, because I have a dream. And the big dream is to combine the real world, physical, tangible evolutionary systems, which you only know in the biosphere, with those that are controllable, which you only know in evolutionary computing. And if you bring them all together, both together, we will get something which I term embodied artificial evolution. Now, why have a dream? I have this dream for 2 purposes, actually. I believe that we can do 2 things if we achieve this. One is evolutionary engineering. And that is the engineering a completely new, radically new way of creating, making things, autonomous, adaptive artifacts. On the other side, we can get a platform, a substrate to do fundamental studies about evolution in general, not just as in carbon. So basically it comes down to making things with evolution and understanding things with evolution. And therefore this controllability is really important, because it gives us the knobs that any experiment needs to continue. My thesis for this whole talk is that there has been a great revolution in the 20th century, which not many people realize or see as evolution, but it was one. Because it actually ported the whole concept of evolution from hardware to software. And we know the emergent, or the field that it resulted in as evolutionary computing. I will spend the first 5 minutes of my talk to give a very, very limited summary of evolutionary computing, and this is the audience where I really can keep it very short and limited, and explain why I think this is a revolution.
Can we turn the volume down somehow?
Somebody is not muted at one of the partner sites and it's interrupting the talk. Can whoever it is please mute?
We need the TV.
Can we turn the TV on?
Yeah, we can mute that.
Yeah, we can
Is it like a
Yeah.
Sorry.
Okay, thank you. So the revolution, yeah. Why I think it was a revolution is because it really turned the concept. The concept of evolution was offered as an explanatory concept. It explained a process that has already taken place afterwards. And by the invention of the computer, it became possible to create words where they could replicate it. So the concept of evolution became a creative concept, a productive concept, rather than explanatory. Afterwards, it became a productive, creative concept a priori. So we use the concept to create new processes rather than explain past processes. Of course, it didn't go in one day. So it took a couple of years and a couple of people, and I don't tell you who these people are. At the end of my talk, you can tell me all the names of all the faces here, and if you know all of them, you may win a piece of Dutch cheese in my case. So these are the persons who were really instrumental to evolutionary computing. But the basic idea, I want to give you the layman version of the concept of how to make a biological concept into a computational concept. And all it takes is 3 digits, 3 steps. The one is the set of individuals. In biology, on this proverbial island, we have little rabbits and the foxes and the eagles and whatnot. We have individuals. In the context of problem solving, we could think of a traveling salesperson problem, and then an individual would be one tool. And we will have a whole population of these tools, and we want to evolve a good one. To do this, we need selection. And on this proverbial island, selection is done by the foxes and the weather and the other rabbits. In a computer science context, we, the experimenters or the programmers, postulate that selection is done by length. Short is good, long is bad. That's it, it's axiom, we put it in the system. And the last and third component is reproduction. To have evolution going, you need to reproduce, you need inheritance, you need a repeated process of creating new stuff. This is all it takes, but mind the big chief with respect to the fitness function. As it happens, in biology, fitness doesn't exist. There is no rabbit out there with 100 on his forehead saying, my fitness is 100. Could we make a little rabbit, please? Fitness is a secondary feature. In the eye of the observer, we associate it with the system. And if a rabbit has lots of offspring, then it's a fit rabbit, otherwise it is not. Otherwise it is not. In a computational context, it's a primary one. We say we determine fitness by length, and if an individual is fit by our measures, then it can make lots of offspring. So it's upside down, it's a big chief, it is not very often explained to computer science students who think that the thing they do in the computer, a genetic algorithm or an evolution strategy, is really something like biological evolution. There are other reasons, of course, why it is not biological evolution, but for me this is one of the most prominent reasons. So having understood all these bridges, if you want to build an evolutionary algorithm, you have to go down a list of things you need to implement, and that list is not that long actually. It basically takes 5 things to do. Identify the phenotypes, the objects that you want to evolve, like tools for a traveling salesman. Design the code for them, the artificial DNA, and the variation operators, mutation and crossover that can manipulate this artificial DNA, the code. And it's important to understand that evolutionary operators always work on the genetic code, not on the phenotype itself. And then you have the quality-related things, and that is a measure for fitness and selection operators that work on fitness information. And there are usually 2 kinds of selection, known under the name pre-selection or post-selection, or parent selection and survival selection or replacement. Putting it all together, you get an evolutionary system. You think. This is what I thought, 20 years ago when I started to do that, and the biologists were mocking me, saying this is not real. And I want to quote a very well-known, well-respected evolutionary biologist who told me the following fact. The whole information of a human would fit on one CD-ROM. Whereas Microsoft Windows needs 3 DVDs. And we are much more complex than Microsoft Windows. So where is the rest of the information? And his clarification for this puzzle was, it's in the environment. What we are is partly coded in our DNA and partly in the interaction with the environment. And anything that does not have an environment or just an oversimplified environment does not qualify for him as real evolutionary process. So this is what motivated me to move to embodied evolution a little bit. So understanding which components you have to implement to have an evolutionary algorithm also makes you understand that there are 2 main pillars behind any evolutionary algorithm and probably any evolutionary process. One is creating diversity by changing what you have, by mutation and crossover. And the other one is reducing diversity by throwing away what you have. That's the selection operators. One is introducing novelty, and the other one is pushing quality. And if you want to make a working evolutionary system, you have to balance these 2. And it's one of the big puzzles and the big mysteries of evolutionary computing, how to do this. Technically speaking, it's in the parameters. The parameters of an evolutionary algorithm regulate these 2 forces, and if we knew how to do it, we would be much further with evolutionary computing. And this is why I think parameter calibration, tuning, or on-the-fly parameter control is one of the essential big challenges of evolutionary computing. So this was the introduction. This has become a very respected field with very respected textbooks. So if you want to know more about it, seek no further, read a good book, and in just 14 chapters you will learn a lot. To tell what I think evolutionary computing has brought us, I want to make just 3 points of the most important properties of evolutionary computing. First one is, first thing we like about it, it can solve very hard problems. Better yet, it can do it better than humans. If you need arguments that evolutionary computing works, you may want to look up the very first number or the very first volume of the journal Genetic Programming and Evolvable Machine. There is a paper in there about human competitive evolutionary algorithms. And they have a list of quantifiable descriptors of some invention, and they compared human results with evolutionary algorithm-generated results. And they claim that they prove that there are quite a lot. And they never gave up since then. I guess the first number was in 2003. They kept going, and I guess it's geneticprogramming.com where they keep this list Hall of Fame. So if you go there, you can find even more. But the second thing we like about evolutionary computing is that it can respond to changes. This is a classic example from evolutionary strategies. What you see is on these 2 curves, on the left-hand side, you see the fitness function changing periodically. So the algorithm is optimizing and it's minimizing something, going down. And then somebody changes the fitness function, which means that the whole population is ill-adapted, so the fitness elevates to better. And then the algorithm is optimizing it again, and somebody changes it, so, okay, we are always fooling the algorithm, and it can follow the optimum. And this is what happens to the mutation step size. This is evolution strategies. The mutation step size is co-adapt with the variables that encode a solution. No human interference or influence is necessary. The system changes the mutation step size according to the change situation. As we all know, in the beginning of your search, we want to make big leaps because you want to sample the search space in a broad area. Once you find the promising areas, you don't want to go away. You want to fine-tune, so you need small steps. And this is exactly what the system does. It brings up the mutation step sizes in the beginning, and as you approach the optimum, it brings them down. And if you change the fitness function, it notices and fitness, the mutation step sizes follow the algorithm in changing the optima. This is really a unique property of evolutionary algorithms. So the third point I want to make, I want to help, and I want to do a little experiment with you. If you did my TED talk, you are out now. Or if you saw my TED talk, then you are out now. If you didn't, then I really want you to think of a very original, non-existing, bizarre animal. Close your eyes and try to visualize an animal that doesn't exist, cannot exist, it's bizarre. Now you can open your eyes, and what you see is something which may resemble very much of what you thought. This is the well-known chimera from the Greek mythology. And I guess we all agree that this is a non-existing animal, maybe bizarre animal, but I wouldn't call it a very creative concept because it's just a concatenation of existing parts. It's a lion and a goat and what else? A snake and some flames. So it's not really original. This is an original animal. And before the discovery of Australia, nobody has ever drawn or described an animal with a pouch. Evolution did. It's a good feature, and therefore it evolved. The creative humans didn't think of it. So closer to evolutionary computing, this is again a classic example from evolution strategies, the optimization of a jet nozzle, a shape which is maximizing something, the throttle. And back in the 70s, this was a hugely controversial result because the winning design was something that a designer, a real engineer, would never have come up with. It's not symmetrical, it's not nice, but it is provably very good. So summarizing all these, the balance about evolutionary computing is, on the positive side, evolutionary algorithms can solve hard problems, and sometimes they can solve them better, much better than humans. They can cope with changes, and they can deliver very original solutions. The downside, there is always a downside, of course, parameter tuning. We really don't know how to calibrate an evolutionary algorithm. People do it by hand, sometimes it's an algorithm, but it's essential that you do it well. And it can take long. Depending on the application, long run times can be tolerable or cannot be tolerable. So it excludes a couple of applications that otherwise could be interesting or possible. So the two one-liners, take-home messages, I always brief to audiences. When the going gets tough, an evolutionary algorithm gets going. If there is no analytical model, if there is no neat provable algorithm to solve a problem, if you really don't know what to do, try evolution, it will help you. And the second one-liner is, an evolutionary algorithm is the second best solver for any problem, which is, to give some nuance to the first claim, if you spend enough time and money, you can always invent a solver for any problem, which is really very good. But if you don't, then evolution would be a very good candidate. So it's not, I'm not claiming, or our community is not claiming that evolution is the best solver for everything, but it's the second best solver, and it's transferable from one problem to the other. During this presentation, I somehow tacitly assumed a certain mindset which you may not have realized as a choice, but it is a choice. I was in the context of hard evolutionary computing. And hard evolutionary computing is characterized by an optimization mindset. It's the result that counts. So it really may be optimization or design or something where you are happy if you get a nice object or a nice optimum. But there's also soft EC, which is more like in the modeling and the simulation mindset, where you really want to generate some system behavior. And it's not the result that is really interesting, but the process. That's what you are investigating. And if you look at the technical differences between hard EC and soft EC, there are quite some. And each and every point I mentioned here represents a specific challenge for the soft EC approach. And in the second part of my talk, I will show you results about each and every one of these. So as for hard EC, fitness is a technical objective. You want to minimize the tour length, that's your fitness. Everybody knows that part. The reproduction loop is entirely synchronized. This is something people know but not always realize. There is a loop, the main loop of the evolutionary algorithm, or an oracle that oversees the whole process, and the population size is kept fixed. If you want to get rid of 10 individuals, you have to have 10 new ones to fill the gap. Or, if you want to have 20 new individuals in your population, you have to kill 20 old ones first to make place. Entities are state and timeless. So a tour in a turning salesman problem doesn't have a state. It's evaluated, and the fitness evaluation may cost time in real time, walk time for us, but for the system itself, it's just an instant. And finally, they can be combined, so evolution can be combined with learning, and it's one of the most successful areas in evolutionary computing, and we call it memetic algorithms. And the analogy with learning is really very far-fetched, but originally it was motivated by that, but the success proves that it really helps. Trying to interpret all these in the context of soft computing, you get a completely different picture. Because in the soft computing mindset, to give you a concrete example, a swarm of robots that is trying to achieve some behavior by working in reality, or in artificial life, or artificial inheritance do the same, they undergo environmental pressure, environmental selection. And they may or may not have an objective from the designer to it. So if we send a bunch of robots to Mars, or some deep space or deep sea exploration, or some deep mining 2,000 miles under the Earth, we may not know all the circumstances. That may be also changing circumstances. So we really want them to evolve and adapt to those circumstances. In the meanwhile, we want them to do something useful. So on the one hand, we tell them, go there and get a life. And on the other hand, we also tell them, do something useful. Send back the gold, or build a house before we come. And it's not really allowed to combine these two. The second thing is, if you have a bunch of things that live and die in a lifelike setting, just like us, then the reproduction loop is not synchronized. If somebody dies, if a human being dies, it doesn't have to be replaced immediately with a baby. And when a baby is born, you don't have to kill the grandfather immediately. It's a completely asynchronous loop, and if you do it in an artificial system, you will have a huge challenge of keeping the population within bounds. Because it might explode or it might implode, depending on what you do. And we just have no information, no knowledge about how to do this. These entities evolve in time and space. A robot is really in time and space. So a fitness evaluation, it's not just an instance. It's not just an abstract measure of the CPU time or something. These really, it takes time for getting from A to B, and it takes time to meet each other and decide that you will reproduce and create a baby. Everything is in space, everything is in time. But the very first decision you have to make as a designer, how long is an assessment? How long will be a robot evaluated before you assign a fitness value to it? If you make it short, then it will be very noisy. If you make it long, then you will not have enough time to have many generations. And the combination with learning is also, it's a long challenge, of course. Who is regulating whom? Traditionally, people are trying to evolve the learners, but it can be inverted, and you can have a learning method which is optimizing the evolutionary process with some fixed success. So, in a couple of minutes, I will give you some technical results based on papers in chronological order. First one about autonomous selection, where individuals decide themselves when they want to live and when they want to die. Then about the combination of learning and evolution in a certain way in an artificial life system, followed by a combination of open-ended or objective-free evolution, where everything can go anywhere, and goal-driven evolution, where you really have a force this force here, which tries to keep everything, a little bit focused. And the fourth one will be about changing the time for fitness evaluations in a real life or artificial life setting. So as for autonomous selection, the problem is known. If you detach the reproduction cycle, then you cannot manage the population sizes, and it's really hard to tell how to tell when to live and when to die. So in a paper quite some years ago, a couple of colleagues from distributed computing and myself made a system and tested a system which did really all this based on a very specific protocol in distributed systems, gossiping. The gossiping protocol is a peer-to-peer protocol that allows individuals to talk to their neighbors, and if everybody does it in a certain way, then each and every member of this population or distributed system unit will have information about the whole system. So they, for instance, they could count themselves, and if they can count, then they can calculate averages. So they can calculate the average fitness of the population with just a very small lag based on this protocol, which is the basis of the whole method. Formally, the method implies that selection is regulated by a kind of distribution, this sigmoid function, which transforms fitness values to probabilities between 0 and 1. Every sigmoid function has two parameters, the n and the s. I don't want to explain you what it is, but for each and every individual, two parameters for survival selection and two parameters for mating selection are sufficient to decide about life and death, or reproduction and death. And the nice thing is, there's a rather intuitive system of managing the individual values for these four parameters in such a way that the population cannot explode and cannot implode. So there are two things in this system. One is individual decisions about when to mate and when to die, and the ability of the system to adapt itself. If the populations are getting too big, everybody will be killing themselves. If the populations are getting too small, everybody will be, making children. So we tested a couple of properties of the system. First and foremost, it is stable. Of course, it goes up and down, but it never gets out of bar. Second, it can solve problems. So it is okay as an optimizer. Second, in chronological order, is the combination of evolution and learning. This was an artificial life system in a European project called NUCTICE that attempted to combine evolution and learning and social learning in one system and do something interesting with it. And we had this problem of the population size management because it was obviously a detached reproduction cycle. So we tried to solve it by adding a reinforcement learning method which would regulate the willingness to mate. And at the first attempt, we saw that the system died because mating was a costly action. All parents had to give a share of their energy to the children to start off. And that means that on an individual level, mating is just not good because you lose a lot of your energy. So reinforcement learning learned all this and made the system, collapse in a few generations. Nobody wanted to mate anymore. But then we figured out that there is an easy fix to this. Okay, so just saw the third bullet point. Additionally to that, removing the reinforcement learning system was also not such a good idea because with reinforcement learning system, the system could be better. But the interesting effect was that reinforcement learning was able to have the system, to keep the system alive, if only we allocated a special reward for mating, which was not useful for anything. Its only goal was to combat the effect of unlearning mating because of its expenses. And of course it was one of my PhD students who said, oh, we know this solution, we call it an orgasm. And it worked, and that's I guess, I didn't check, maybe the best cited paper of the whole project. It always goes down with reviewers and all that. So in chronological order, now we are in 2013, and in combining objective-free and goal-driven evolution. There is a simple solution for this if you realize that if you have two priorities and two places where you make a selection, you can just allocate one of those selection moments to cover one priority and the other selection moment to cover the other priority. So this is the main idea. Parent selection can be done by task performance. If two of these robots or AI beings meet, then the decision whether or not they want to mate with each other will depend on how well they perform given the task. And survival selection will be done by the environment. So unfit individuals will not survive. We did this, we combined these two in a system, and we extended an existing system from some French researchers in Paris with a specific mechanism which is multi-objective and open-ended evolution, and tested whether the system can keep the population alive, viable, and do something useful too. These are two curves. Viability we measured by the number of inseminations. So these little robots could walk around in a big arena, and they had to be in each other's vicinity to mate, otherwise they couldn't exchange their genomes. So viability was just simply really how many children can you get, like the rabbits in a real situation. On the other hand, we measured also task performance, which was simply just collecting bugs. You could say it was foraging. And as you see, viability was not affected when adding this mechanism for task performance with reproduction, but task performance was. You simply said it proves the idea in one setting at least. But the fourth one is the last technical one I bore you with, is self-adaptive fitness evaluation plans. So as I explained, the problem is that we don't know how long a fitness evaluation should be if everything is embedded in real time. In a slow robotic settings, we try dynamic environments, challenging the system with the dynamics too. Also, with the mindset of, if it's a static system, then a human designer may come up with some optimal evaluation length and then wipe other. But if the system is really changing, then the human cannot enter the system again and again and again and recalibrate this parameter. So it had to be adaptive or self-adaptive. And pretty much motivated by evolution strategies where this mutation step size sigma is co-evolving with the other chromosomes, we did the same with a different mechanism, and the variable which we call tau was self-adapting with the controllers of these robots with astonishingly good results. So what I show you here is 3 different scenarios, A, B, and C. And for each of these scenarios, 5 different systems with 5 different values for this parameter, short evaluations, pivot evaluations, and one system where it was self-adapting. So the red arrow always points to the self-adaptive system at the end of the evolution. I is big, I is good, okay? So this shows that it was second best. It's also second best, second or third best. So this tells us that the idea works. If you never be the best system, but you never wanted to be the best system, it gives you decent results. And you can really make bad decisions, and it doesn't make those bad decisions. And on these curves you see the dynamically changing environments. So if we concatenate these different words in any order, A, B, C, or B, A, C, you see that the fitness changes, of course, so pretty much like the example I gave you about optimization, but the system recovers, and also this self-adaptive system really brings us sometimes to the highest level of quality. So this is how to do it. You can self-adapt it, and then the system will take care for it by itself. So far, the issues of going from hard DC to soft DC. So the next issue I want to address is embodiment. Even in these, in these robotic settings, what we evolve are typically controllers, code. It's software, it's a piece of software. It is embodied in a piece of robot, but still it's in a digital space. If you look at embodiment, then you realize that there are two things that can be embodied: the process of evolution and the end result of evolution. What we normally do in evolutionary computing, the process and the result are digital. Evolution optimization of tool length, for instance. Sometimes the process is digital and the result is physical. So I know people who evolve furniture and they have it built. Mark Scholler in Paris has one. He has a chair. And Peter Bentley in London, he has a coffee table. And they were both evolved in a computer and built, so they became physical in this way. And my dream is here. Evolution also takes place in the physical reality. But I couldn't figure out a meaningful thing for this, so this may be a good intellectual challenge. Try to find out whether this can exist, and if yes, how do we call it? So if you go for this, then you look into the second evolution, which is my claim. This will take place in the 21st lecture. This will distinguish the first one, which quoted evolution from hardware to software, and now we are going from software to hardware. And the new thing will not be evolution of computers, because it is not in the digital space, so it could be the evolution of things or embodied artificial evolution. So this is division, and there are some very nasty questions about this vision. First and foremost, why? Why would you want to do that? Who cares? And my best answer to that is like, I don't really know exactly. I cannot come up with the killer application that meets this, but there are other guys who had the same problem. For instance, this guy who wanted to build flying objects. And he lived in a beautiful age. He could do his thing without writing grant applications and proposals, arguing for societal relevance and significance for industry and things. But even if he had to, he would have never come up with this. And this is what it was. Flying objects, we have them, we use them, and I wouldn't be here if we didn't have these things. But this is not why he did it. I don't want to compare myself to him, but the mental mindset is similar. It will lead to something good in 500 years. I just don't know what. Second very nasty question is, okay, how? How do you like to do that? It's completely impossible. You cannot have two chairs reproducing and making a baby chair. And my answer to that is, it's not as far-fetched as you may think. Actually, there are three kinds of people, three approaches working on this. One of them is the bottom-up approach. The chemists are trying to create molecules that are more and more complex, still manageable, controllable, understandable, until they get self-replicating. So they have the whole life cycle for bottom-up. And they have the biologists who do the same top to bottom. They take a living cell and they try to strip, everything out of it until it gets, simple and manageable and understandable, but keeps the property of self-replicating. And then you have the third kind of guys, like roboticists, material scientists, the 3D printer guys, who try to attack the problem head-on and try to make a system which has objects that can self-reproduce. And this is my bet, obviously. I'm not a biologist, I'm not a chemist. All other approaches are just as good, it's just that I would bet on this one, meeting this challenge first. So we had the why, we had the how, and now the what. What would it bring? I said I don't know, in 500 years something will come up, but of course I have some ideas. For instance, if we can evolve robots, or including the morphology, we could have robotic pets, or robotic explorers, or deep miners, or whatnot, that will be evolved not only mentally, not only their controllers, but also their bodies will be evolving. If you go down the scale, you could have nano or micro robots in medical applications. So we could have our personal virus scanners. We could inject ourselves with some robot colony that will evolve to our own metabolism and take care of us, fighting germs and cancer and whatnot in our bodies. The most far-fetched idea, which I got from Steve Rasmussen actually, based on the second Neumann machine, the universal replicator, we could have networks, personal replicators that would be biggish, boxes in our homes that could produce an object. If you tell it, I want to have a glass, or I want to have a controller, I want to have a chair, a t-shirt, it could make and build all of these. And you will be the fitness function. If you put it back immediately, that's not good. If you are wearing the t-shirt for 2 weeks, okay. If it's still not returned after 1 year, then it's a very good one. Because everything is network now, these will be networks. There will be the whole internet. So these designs can cross-fertilize each other on the globe, and there could be trends which we could call fashion, evolving these new things. And if you look at these examples, then there is a huge difference between sunglasses and medical microrobots. The difference is evolving bodies or evolving bodies and minds. The second one is, orders of magnitude more exciting and more hard. And it could lead to something very, very unexpected, which I will tell you in a while. So the evolution of things has the same list we have to go through as building an evolutionary algorithm. You have to decide about the physical objects. You could say, okay, I'm going for robots, or I'm going for virus scanners for the human body. You have to invent the genetic code for those little guys. But the good news is, each and every object which humans make these days has a blueprint. Everything exists on the drawing table first. So this is not such a big step. It's not like we start from scratch, except that those blueprints are made with production in mind, and the one we need has reproduction in mind. So the blueprints and those drawings have to be mutatable and recombinable. And that's not trivial because it could be a good blueprint for production, so somebody reads that and then can build this table, but it is not to say that if you get 2 of those, you can easily combine them into a third one which inherits properties of either of them. So the good news is everything we build has already a blueprint or code, but it's not optimized for reproduction. And then we have to have real birth. And of course also real death. We have to remove objects that otherwise it will populate the whole Earth. We definitely need autonomous selection and environmental as well as classism fitness options. So this is a very long list. And this is why I think that evolutionary computer scientists can play an instrumental role in this process, because we have been there, done that in an oversimplified setting inside the computer. However, this is not as simple. There are some grand challenges ahead of us. What kind of bodies and what kind of code? Once we decide how to start, so what will be the birth protocol? How do you make the first child? And if you talk about how to start, you also have to think about how to stop. Speed of evolution is an issue because life had billion years to come to the Homo sapiens. Probably that will not make a good industrial project. I can't imagine that money for a project that will, give you something in a billion years. And the co-evolution of bodies and minds is one of the big challenges. So I won't tell you about each and every one of them, only 2, the red ones, how to start. I'm really keen on, even in a short talk, addressing this one because of, my ethical concerns. So ethical concerns are for all ethical scientists, but it doesn't always go well. We had radiation concerns. In the 1940s, there were right scientists working on a technology that can be really lethal in your own hands. A few decades later, there's something else. Biohazard, biologists, viruses, biological warfare. from Gusz Eiben. And in a few decades from now, we could have a third one. Robots are. Think of robots that can self-replicate. You may be familiar with this concept of the grey goo scenario, or runaway evolution. So the grey goo is a friendly one, because all it says that the grey goo will assimilate all matter on Earth, and it will be so big that the whole Earth will be grey goo. Runaway evolution is much worse, because it can change from a grey goo to a hostile grey goo, or a poisonous grey goo. It can evolve into something which is really bad. And it's not only killing by the mass, but by what it does. So what I try to emphasize every time I mention this vision is that you shouldn't start before you know how to stop. You always need a kill switch, and it will be very short-sighted to start saying, oh, we will solve that problem when we are there. It's not good enough. Developing the technology from scratch with this in mind is necessary. Otherwise, evolution will, sneak and find a way around it. This is a very small detail you probably didn't notice in Jurassic Park, but when the first visitors get there, they say, okay, but what keeps this system, in balance? And they say, well, we engineered them in such a way that there is a food supplement they need, otherwise they will die. Okay, so if they kill all of us, they will die themselves because the food supplement will not be supplied. And then later on in the movie you hear that evolution got around it, and there are dinosaurs who do not need this food supplement. So that's not good enough. There might be something very fundamentally better than that. And the second issue is the co-evolution of body and mind. I can imagine that you have seen things like that in artificial life, but I'm quite sure that you didn't go this far, as I tried to do it here. If you can evolve physical bodies, it comes down to evolving hardware. At a certain moment, you will get an architecture that will be non-formal architecture. Every computing device we have is based on the formal architecture. The good old processor, CPU, and memory, and peripherals and whatnot. But our architecture is not like that. So if you change the hardware architecture, there will be also a new kind of software. We know that programming a neural network is completely impossible. You have to teach or educate it somehow. So if you change hardware, you will have to change software. You cannot put Java code on the new hardware because it will not accommodate Java code. So the notion of program, the notion of programming, the notion of software engineering, debugging and verification, it will all change. So if you go down this alley, computers and computing will never be the same. To put it with a piece of, it's not disrespectfully meant, but formal is that. The formal architecture will be just one of the possibilities. So scientifically, how can we get there? I said I'm betting on not the biological, not the chemical, but the hardware-based approach. I have an idea about one possible framework to realize this, which is coined and named, dubbed the triangle of life. Actually, it was born out of the Singular project. You might have seen these pictures already. It's an EU research project which finished 2 weeks ago, after 5.5 years. And the vision was to have physical robots that can aggregate into a bigger organism. So they were all autonomous, capable of locomotion, and everything a robot does, but they could aggregate into a bigger organism, give up their own identity, and become a cell in a multicellular robotic organism. So Symbio never got there for various reasons, but it at least inspired us to come up with a framework. And this framework is a generic framework, so it is not necessarily restricted to modular robotics. What it does, it decomposes life into 3 stages, and thereby it provides guidelines for implementation of lifelike properties. And on a theoretical level, it defines a whole class of AI systems. So to tell you how it works, and it goes far beyond Symbio. So I just want to make this clear that Symbio never really got there, not even in simulation, let alone in hardware. So the triangle of life is this. And one thing to notice that it revolves around the notion of conception. Normally you would say the cycle of life is between birth and death. But if you are evolutionary speaking and thinking, then this is the pivotal element, not death. So imagine in terms of modular robotics, because it's easy to visualize, okay? Imagine a bunch of little robots, and at a certain moment they decide to aggregate, so they start to recruit each other, because one of them has a plan. One of them has a piece of digital DNA, a blueprint that describes a certain body. And it recruits others to join, and during that process, the morphogenesis process, the organism is just being born. When it's ready, it's delivered. So that's the moment of birth of a new organism. And obviously, if it's a child of two existing organisms, then the existing organisms have proven themselves, so they have a matching body and a matching good controller, and the body mesh physics. This does not need to be the case for the child, of course, because they are both recombined and probably mutated. So this child has to be educated. It has to learn to control its own body, just like, a little calf stands up and tries to move, and then in 1 hour it can. Same for robots, and they may be forced to learn lots of other things. Going through this learning stage will bring them to a level where nature, the user, the experimenters, some built-in protocol will say, okay, you survived so far, and you achieved a certain level of skills, and therefore you are fertile. From now on, you can also reproduce. And if you meet somebody whom you like, you could make a child with that other organism. And that's where, grown-up life, nature life starts, and this is where you, just survive, collect energy, try to propagate your genes, or if it's really a man-made system for something useful, this is where you have to perform your tasks. And once you meet somebody and you agree on creating a child together, conception takes place, either the parents or something, some mechanism starts with breathing an organism. So this is the cycle of life captured in just 3 stages. And I don't think you can do it with less than 3. You couldn't do it without this, I guess. You cannot do it without this, and of course this is why you are doing it. So 3 is really the bare minimum. Obviously you could make it 4, 5, whatnot, but you cannot make it 3. So this is, again, a generic concept. It could be realized or incarnated, implemented in modular robots, but it does not need to. Once we get there, we could prove the whole concept. And not only the cycle of life concept, but we could prove the whole concept of evolution in physically and embodied and embodied real space, real time organisms. To my knowledge, nobody has ever built such a system yet. Could take, 3 years, 5 years, 10 years, but somebody will. And once we will do that, it can change a lot of things around us. It could be a game changer in evolutionary computing. So evolutionary computing really has to reinvent itself. We don't know a lot of things, but actually we can solve a problem. Give us a problem, and sooner or later we can come up with an evolutionary algorithm that can solve that problem. But this is orders of magnitude harder, so we really have to rethink again how to design the genetic code. In old-fashioned terms, what is the good representation for your problem? How to calibrate selection and variation, the push towards quality and the push towards novelty, and lots of things. So it will be a new challenging era for evolutionary computing process. It will also open up a new area of studying evolution. We will have, a completely new substrate, and whatever we learn in that substrate, if it's the same as in biological evolution, we will have a much better reason to say that's really fundamental. That's evolution. It's not just happenstance. It's just not that it happens in carbon on Earth, but it must be so because it's a completely different. It's just a second example, but it's much better than theory forming based on one example. Design and manufacturing could be completely different. If all these artifacts around us are not designed but being born, that's a completely different cycle. It's a completely different way of creating stuff. And finally, you know, the formal one is that argument. Computing and computers will be completely different at the end of the road. As for me and everybody, there is a long, long way to go. And I have a personal history in projects that inspired me, and some were, you know, aiming at this. Distributed resource, evolutionary algorithm machine. Well, that was new kind. It's a variation of something like evolutionary, social learning, individual evolutionary and social learning. And then we had Symbiont, you know, the robotics project, modular robotics project, Embodied, which was a kind of pioneering project on embodied evolution, not doing research, just workshops in identifying the challenges. And Evo3, which unfortunately was just a proposal turned down, building such a system in physical reality. I don't give up, so I will go on and hopefully so with you and so with a lot of other people, so that we can do it together. And doing together means also big leap ahead. This is how I see evolutionary computing compared to architecture. So yes, we have the building blocks. Yes, we can design and we can construct, and there are beautiful things coming out of it. But that's not the real thing. This is the real thing. This is what we can do now, and this is what it takes to get there. This is the difference between evolutionary computing as we know it, and embodied artificial evolution, or the evolution of things as I would like to have it. Once we get there, there will be several changes in life. I will fantasize or speculate about three of them. Gadgets will become active. So everybody has gadgets here. I bet that in this very room there are more computing devices than Homo sapiens. I have got three, you know, the phone, the iPad, and the MacBook. Probably everybody has at least one, but probably two, three. If these embodied things will come by, they will be around us. So there will be one on my shoulder, one flying around my head, one sitting in the corner, watching you. So if I gave this talk in 50 years, I could, maybe I would say, there are more embodied agents, artificial agents in this room than human beings. So that will make a completely different hybrid society. We are used to our devices being not autonomous. They have to be, you know, controlled and commanded by us. But they will be autonomous, so it will be a new society. Probably we will also a new economy. Think of horses and dogs. Somebody who has a good bloodline can make fortunes just simply, you know, letting that dog or horse making pretty dogs and horses with good skills, or good looking ones, or clever ones, or fast ones. With these gadgets, it will be even worse, I guess, because it will be on a much bigger scale. I have a nice gadget, and said, you always tell me, can I have your gadget fertilize my gadget so that we could have a better gadget? And I said, yes, it costs $2,000. So that will be a new economy. And finally, new legislation, because if evolution will be kicked off by humans, then somebody has to be responsible for what it does. At the moment, if there is some, you know, baby born or an animal born which doesn't satisfy something which you want, then nobody is responsible. It's nature. But if you have an evolutionary process that does things that are maybe not legal or not wanted, not desirable, dirty or disgusting, somebody has to be liable. Who is that? You know, the firm that built it, the factory where it came from, or the object itself, or the owner who educated or guided that thing to evolve to that, or the worst possibility, the guy who developed the evolutionary algorithm. completely unanswered question, but this cannot be an economy on a large scale before we also solve the legislation problem. So I wanted to close this talk with conclusions, but there are no conclusions here, really. I can make concluding remarks. First and foremost, matter matters. If you take evolution out of digital world, it will be a completely different system. Second is, code is king. Everybody in evolutionary computing knows that if you don't get the representation right, you can never have a good evolutionary algorithm. And no matter how genius you are in getting mutation and crossover and selection, if you don't have the right representation, it just won't work. On the same note, we have to have the good code for these objects, which is tailored to reproduction and not to production. And finally, I really think that this will be the next big thing. So we have great inventions, the computer and everything, the internet, and I believe a huge change in the coming decades will be this artificial evolution around us. And what this huge change will mean for all of us is really a big speculation. And if I try to answer it based on the only known example, real evolution, then I think of this. This is the timeline, and this is how life on Earth started to evolve, and then it led to all this diversity, and this is where they are. Thinking of this, and trying to answer the question, where does it lead to? The only right answer is, I don't know. Really like to see that.
I think we should unmute the TV.
So, very nice talk. Thanks a lot. I just want to ask a little bit about what you meant with this notion of everything will never be the same, right? So I think that would depend upon kind of what the level of analysis is. I'm someone who thinks that von Neumann will never die, right? So, and because you really talked about this at such an abstract level that it seems to me as though those concepts that you mentioned, programming and so on, really have to remain the same at that level of abstraction. So I'm wondering if you have something else in mind, or you really think that even at that very, very low level that there will have to be changes. And you could just try an example and what you have in mind.
I don't know whether I have an idea about the architecture itself.
So for example, certainly we would know that different languages would change and such things. But the idea of programming itself, right, in the Neumann stuff, it seems to me as though that would, but it seems like you're making a stronger claim that really even at that level it would change. So that's what I'm curious about.
Okay, I think I understand your question, and if I do, then I have an answer. And the answer is that programming will be more like teaching or educating, rather than writing code directly and doing the unit tests and all that thing. We will have syllabi. Syllabi. We will have syllabi, and we will have to coach, a being through a syllabus to get there gradually. And rather than doing unit tests, we will have examinations. At the moment, airplanes are mostly driven by computers. So if the plane flies 10 hours, I guess 8 hours, it's the computer driving or flying. 2 hours, it's the humans. So we trust a lot to them. The human is in charge, and the pilots are really mission critical. And they are examined like every year, I don't know exactly, because we want to have them certain skills, and we trust our lives on them. And I guess this will be the new mindset for these objects. So if you want to have a whole colony of robots in and around your house, doing really mission critical things like babysitting, not the cleaning one, but the babysitting one, and taking care of your grandma, then you really want to make sure that they satisfy the conditions, safety conditions. And the only way to do it, I guess, is teaching them. You cannot just code them. That's one of the things I really believe. And given this, you have to examine them. So it will be pretty much like educating students rather than sitting down and writing code.
So, if you don't mind, I'd like to reserve something you said at the beginning. If you addressed it later, I'm sorry I wasn't paying attention later, so I was thinking about that. But you said this thing about rabbits, for example, don't really have fitness. They don't have a number on their head, right? So I'm going to ask you a question, and I do not intend for it to be snarky. I apologize sometimes, but do you think that rabbits have mass?
Rabbits have
Mass. Mass.
mass,
Yeah.
like kilograms.
Yes.
Yes.
What's the difference? Because suppose I say no, rabbits as well as other organisms have fitness just as well as they have mass, and the difference is that you can only know the mass by going out and measuring it. And when you measure mass, you put the rabbit on a scale. Yes, you don't do it while it's running in nature, right? Because you have to do it under idealized conditions. And if you want to know the fitness, you do exactly the same thing, except there's no scale. There's other measures. So my point is that no,
Yes, yes.
rabbits do indeed have fitness. There is a fitness there. There is just not enough. It's just very hard to measure. But it's exactly the same as
Very
mass.
good point. Yeah. I like it. This is a really very good point. So I cannot tell you, no, you don't see it right, because I think you really do see it right. But there is a difference still. When I'm rephrasing the same claim somehow, in an artificial evolutionary system, it is a primary measure. We build a system where fitness is determined first, and that determines the chances for reproduction.
So that's the same if you do a physical simulation of, say, in astrophysics or something. You just say, oh, this particle, it has mass. But that you prescribe it. And therefore, because it has that mass, it affects the environment this way or that way and so on. It's exactly the same. But nobody will not say that the electron has spin. Spin is a good example because nobody knows what spin is. We just know how it affects the environment of the electron. But it's the same thing with the electron's mass, and we think we know what mass is, but we don't know any more than spin or fitness. It's just how they affect the environment. And we can only know them if we measure them.
Very good point. Yeah. Thanks.
If I may add, I think that's a good point, and most of the natural systems have not one fitness, I think. So he's talking about mass, he's talking about some other performance that the rabbit is supposed to do, and you can have another metric there. So I don't think the nature is just working with just one particular fitness.
No, of course
And
not.
many of our work in evolutionary computing, we try to associate an individual with one fitness, and that sometimes is a problem. So
That's one of the differences. Of course, it's you saying this. There are more objectives.
But the thing is that, if you look at natural systems, you can't just say, okay, there is only one fitness that everybody is trying to maximize or minimize. And there are always more than one, and then that's the problem. That how can you have selection based on this one?
Of course, so to get a child, you need to be rich and famous and beautiful and all this. Yes, but actually, to this point, it's really a very nice point. So I keep thinking about it.
Maybe a much more specific question. I was just intrigued by these, I think you call them these conditional, these sort of the self-adapting fitness evaluation times, the tau.
Yes.
I'm just curious if one was to make these not a sort of parameter but a conditional thing, so you could take in actually information from the environment. Let's say you had a cycling environment, A, B, C, B, A, C, whatever. If you could actually use the system to reveal sort of what types of problems could be solved together. In essence, the organism, when it wasn't up to the challenge, could go into dormancy, basically have a high tau, not get evaluated, and then start becoming evaluated again at other times. So whether or not if you build sort of plastic or maybe a learning mechanism into these, this is my first exposure to hearing about these. I wonder if there are any ideas to do things like this.
Yes, I think it's a very good insight, and actually the only other example I know of is the mutation step sizes in evolution strategies. And the evolution strategy guys really believe that the sigmas carry information about your fitness landscape. They call it the local topology. Because in some very complicated version of the whole idea, the sigmas, they are elliptic. Okay, so the sigmas, if you have one sigma for each and every coordinate, that's a prerequisite, then you have as many sigmas as variables, and the step sizes in each direction tell you whether you are, already at the hilltop or you are still climbing. And you put it all together, you really get an information about the local topology, not about the whole fitness landscape. So based on that analogy, I can imagine that this Taurus self-elect, and they give you some information about the fitness landscape somehow. We just started, so we have no idea what it says and how to read that, but it is definitely possible.
So I'm going to preface my question by saying I am not a computer scientist or a computer engineer or physical engineer or anything like that. But one thing that I was just kind of thinking about, I think this sounds like super cool, and even if it just sounds super cool, like on its own. But like one of the things I'm kind of wondering about is like, so evolution takes like, as you said, it's taken billions of years, and what we see is really a limited subset of all of the possibilities of life that have sort of been selected for by the environment. And what we don't see is, or we don't see as much, is all of the unfit organisms that sort of, fell by the wayside before they could reproduce. And it seems like in this situation, like, it's still human intentions that are sort of deciding what the evolutionary challenges for the organisms are. And this is probably a really bad example, but the example I thought of is like, I don't necessarily think of like it being super productive to like wait till whatever varying materials come together and mate and reproduce and have the right combination of genes so they eventually make it a toothbrush, versus like, I know exactly what I need my toothbrush to do, so why don't I just go design a toothbrush? You see what I'm saying? And especially in the sense that like as humans, we have this really super highly evolved capacity for design, for efficient design, for particular tasks. It just almost seems like, you see what I'm saying? Like it's almost like we're introducing a lot of chance and elements and sort of letting nature, which we really don't control that much, like go on its own until it comes up with the solutions, rather than just like, we're getting really, really good at just designing solutions to particular problems on our own.
But I guess this would not be the most efficient way of designing toothbrushes. So there is something I didn't mention, that's the economy. So the economy might not pencil out. It could be possible to evolve, new kind of toothbrushes, but it might not be economical because it will be an awful lot of waste of time and energy and matter, raw materials and whatnot. So it could be that it will never be done for economical reasons, but not for conceptual reasons.
But then in your hybrid society,
Yes.
okay, are we going to be patient enough to wait out the robots evolving something that's...
Yeah, but it might not be that radical. So we are not talking about the toothbrush popping up in a society where there are no toothbrushes. Okay? We may talk about robots that are good for something and change their morphology to be better than that something, or they get a new morphology, or with the same morphology they do something else. It's a far-fetched example, I really don't know if this makes sense, but it could be that you would have robots for surveillance, and all of a sudden they bump into your window and somehow they clean your window, and you figure out that your swarms, which you first only used for surveillance, they are very useful for cleaning your window. And then you enforce that, and then you will have a branch of a subspecies and a species of flying swarms which don't do surveillance anymore, but they are cleaning your windows all the time.
It seems like something like this would be most successful, though, with a combination of human-driven engineering and evolution. So, I mean, in the toothbrush example, you would actually build a toothbrush, and it would be relatively good, as good as toothbrushes are now, and people would use it. And then as better toothbrushes come around through the evolutionary process, they get selected by people wanting them and using them and reproducing that way. And then those become more popular, and so the toothbrush would get better and better, or whatever you're trying to build. And so you would have this combination of human-built things in a system like this,
with variations on those that are typically chosen because either they're better at what they do or they interact with humans better, that there's some quality about them to improve them. And then occasionally something brand new would naturally emerge out of the system in a basically speciation event that would end up getting selected for in a new niche. And I mean, that's how I would expect it to go. But without the human intervention, I think the process would just take too long to get to useful
I
things.
really want to tell you something which you may have misunderstood about me and people like me. I definitely never say, like the opposite, that you always have to evolve solutions to problems. I always have some people come in, I have an industrial problem, I learned about genetic algorithms and I want to go to work. If you have a solution already, just use it. If you know how to solve the problem, solve the problem.
Right.
Don't use evolution for the sake of using evolution.
It's the second
Even
best
if it's a
approach.
big, huge, complex problem, you don't have to ever optimize everything by evolution.
Sure, thank you.
Definitely not.
But what you want is to evolve the undesirable.
Yeah.
Right.
So, your turn.
In terms of whether or not physical things can actually do useful evolution, like there maybe like a back of the envelope calculation would be how many generations do you need, and I don't know, from computer evolution, you need 100,000 generations to do something useful, and if you want something to happen within a year, then that's like 1 generation per minute or something. So you'll need something that could replicate itself once per minute. It has to grow up in a minute.
Nobody knows. I want to say two things about it. One is the kind of, the funny answer. It's like students of me, okay, but how many generations it takes? How many fitness evaluations it takes? What a question. How much money does a car cost? And you say, oh, well, it depends on what kind of car, so that's what they understand. That's one thing. The other thing is that we definitely need accelerators, so speed up evolution is slower and everything like that. And there is quite a good way of speeding up, and that is, in evolution computing, we call them surrogate models. So the good thing is that you can build this surrogate model is an abstract model for fitness landscape. And what it does, if your fitness evaluations are very expensive, then you can do a couple of generations on the surrogate model, as a thought experiment, and then make, the real thing just every now and then. And when it gets physical, this may be even more important than just simple evolution optimization with expensive fitness landscapes. And we have very good examples that it works. How Gibson did such a thing, when the robot really learned about itself and the environment. So my technical answer is it would be very often probably too slow, but we know a couple of tricks that may speed it up big time.
So another question I have is sort of a more general question, but I think it has interesting evolutionary implications, which is like, do you see this sort of as maybe like a radical speciation? Like, in other words, there's going to be a completely radical re-engineering of computer science and computer engineering, or do you see this sort of like coming out of, say, the like RepRaps, like the 3D rapid prototyping printers, because there's sort of a way, right, where like people can print stuff and share the designs through the internet, and I can say, oh, dude, that bottle opener you sent me, you need to like change this dimension, and now the bottle opener we better. So do you see this coming as like a natural, like a sort of the process of gradual change, sort of as the field is currently, or do you think this is like really sort of a radical reorganizing of the way we even think about these things?
I think it will be radically different, but it's not overtaking or replacing our existing systems everywhere. It will exist next to it. So once again, we don't want to evolve everything all the time, and we don't want to do everything by this technology all the time. So I think it's still a completely legitimate approach to say, I want a cell phone. What does a cell phone need to do or have or something? And then you design a cell phone to some extent, or maybe the big parameters, and then let the other ones evolve within